Welcome back to learnpiezo.org. And last time we left off and we finished more or less talking about the K squared, the electromechanical coupling factor, electromechanical coupling. And we saw that it was equal to the stored energy, or it was equal to the converted energy over the input energy. We learned the difference between stored energy, converted energy, and input energy. So this time, I'm going to speak a little bit more about in detail about the properties of piezoelectric materials, namely the compliance and the permittivity. So actually, in piezoelectric materials, there are two types of compliances. What we call the compliance under constant electric field and the compliance under constant dielectric displacement. And similarly, we have the permittivity as the permittivity under free stress and the permittivity under free strain. So we're going to be talking about why these affect the properties. So important note: boundary conditions. Affect the properties. Both electrical and mechanical. Both electrical and mechanical boundary conditions. So you can see, look here, we have electrical boundary conditions affecting the piezoelectric, the elastic compliance, the mechanical compliance, and we have mechanical boundary conditions, mechanical conditions in the material affecting the permittivity. And we're going to explain this now, why this occurs, why we have a difference of boundary conditions affecting the properties. So we'll start with the elastic compliance. And I want to bring your attention back to the piezoelectric plate we know and love. Okay, so let me draw a little bit differently. Let me draw it like this. Let's see, electrodes on top, and we have the electrode on bottom. So, and then what we do is we connect some wires to it, so we can kind of get the potential, and we apply some voltage, and then we say the height is let's call the height L for length. So actually, no, I'm sorry, don't apply a voltage. So consider these two situations. Okay, the first situation, we short this. Basically, the top and bottom electrode is shorted, so we don't get any stored charge. So short circuit. Because normally, let's take a normal piezoelectric material, which is not shorted. Normally, if it's not shorted, if we put a force here and we pull a force here, we're applying a force to the material, and we're applying a pressure, or aka a stress. So we have a certain charge associated with that stress, correct? So we have, let's say, positive charges on one side, negative charge on the other side. So we get this positive and negative charge, and this also results in converted electrical energy. But now consider this case again. We shorted this, right? So the positive charges are going to go to the negative side, or the negative charges are going to the positive side, whichever one you want. And basically, you won't have any potential across the material. You shorted the sides, so you don't have potential. So basically, you don't have the stored energy anymore. You don't have any electrical stored energy when you pull the material. when you put stress on the material. So let's see what actually happens. So we have this stress, we connect the two sides, and then we see, okay, we apply stress to the material. Then basically what happens is that we have the strain is equal to the SX plus, what's the other one? DE. So in this case, the electric field is 0, right? Because if it's the electric field is 0, so we can cancel out. So what we're left with is this equation. The strain is equal to the stress times the electric field, and we get no, see this D, we get no charges appearing. Charge can't appear because the electric field is set to 0. And the other case, we have what we call open circuit, or a constant D, or constant dielectric displacement. So let's take a look at that case. So we have our material again. So electrodes on top and bottom. And this time we apply a stress. Okay. And we get both electrical energy and mechanical energy. Because we have charges on the top, we have charges on the bottom, we have some electrical energy in there, we have some mechanical energy in there. So let's take this first example. In this one, we apply a stress, we only got mechanical energy. In this one, we apply a stress, we got mechanical and electrical energy. Right? So we basically have to stores more energy, then you could say, and we'll kind of explain this now. So in the first case of a short circuit, in the short circuit condition, you're not storing mechanical energy. I mean, you're not storing electrical energy. So again, short circuit, no stored electrical energy. So therefore, when you are introducing strain into the material seems softer. And softer is a higher compliance. Higher S. So the material seems softer. And the reason the material seems softer is that, let's say you have a material and you stretch it L. Okay, you stretch it delta L, and it was L in the beginning. You stretch it that much, you'll actually have to, in this case, you won't need to store any other mechanical energy. I mean, you won't have to store extra electrical energy because you shorted the sides. Because you short circuited, you don't store electrical energy. Therefore, when you're pulling on it, and normally when you're pulling on it in an open circuit condition, you both have to accumulate mechanical and electrical energy, so it seems really stiff. Because you have to, because if you introduce, let's say, 5 microstrain, that 5 microstrain is both going to cause electrical energy and mechanical energy to be developed. Therefore, it seems stiffer. Lower compliance. So this is why materials seem stiff, and depending on the boundary conditions, you could have a stiff, configuration, which is denoted by SE. SE is the soft condition, because there's no stored energy, no electrical energy stored. And SD is the the tough condition, the stiff, because you have both electrical energy and mechanical energy is being stored due to the strain developed. We'll continue in the next video.